the equation, so you have to solve. So the question is that what numerical method to use. So the first choice might be FEM, but at that time I was looking for large information problems, so I was looking at mesh-free methods, and there are a lot of mesh-free methods available. So I skipped this part because in the interest of time. At that time, the most important famous one was the element-free Galerkin method, but the bandwidth is large and it is slow, so I moved on to other techniques, but they also had different problems. We have SPH, we have expert of SPH in the room, so there are different options, but I'll just talk about the one that I used, which is, I ended up using this technique, which is called smooth point interpolation method. I'll just give you the main idea. So the idea is that you smooth the S train. So you got the S train defined as the gradient of displacement, so you can smooth it over an area. So you pick an area and you kind of smooth it. So you average, so 1 over area integration of this. And what is the benefit? The benefit is that if you use divergence technique, then the integration over domain can be changed to integration over the boundary of the domain, and you get rid of this differentiation. So there's no differentiation involved. And you can use different areas to do this smoothing. And so the benefit is that if you think of like a second order governing equation, which we deal with in computational mechanics, when you apply divergence theorem once, it gives you the big form and like the finite element method, and you get a lot of benefit by applying this divergence theorem. You smooth out everything becomes more stable. So the idea is that if you apply this one more, you probably get again one step more like benefits. And no differentiation is required. So there's all theory behind that, which I skipped. But basically the idea is that if there's no differentiation, you can remove some of the error, because most of the error, as you know, comes from differentiation of a function, not from the approximation of the function. So I'll go through this quickly. So basically, in terms of efficiency, computational effort is in the order of FEM, but efficiency is in most problems higher. The benefit is that, I'll summarize the benefit at the end, so I'll skip through this, but the benefit basically is that it is more flexible than finite element method. Then we discretize the equation in time and in space, and we come up with fully discretized equations. So again, there's no point if I go through that. You can refer to our paper. Verification, again, I knew that I was running behind them, be running behind. So I just skipped just a snapshot of different examples that we have. So don't go through in any of them, but we tested this. We even extended to modeling discontinuities, but in a single phase only for now. And also modeling, so I kind of present all these different discontinuities. We also implemented the adaptive analysis, so it is very, very good. The technique is easy to kind of add adaptivity on top of it, because flexible, and it is also good for large deformations, because you can put it in a framework like particle finite element method, and that's what we did, and we developed this for the large deformations, kind of like a particle finite element method, but with this smooth point calculation method. So some conclusions. Sorry, I had to kind of rush through it. I knew the materials. I just wanted to give a snapshot. So basically, we developed this fully coupled based on SPIM. I just finished with some key points of SPIM. So there's no Jacobian in this technique. So the large deformation can be handled easier. You still need this background mesh. There's no direct differentiation of shape functions, so you don't have differentiation. Numerical integrations are at the boundary of the smoothing domain. So basically, you reduce. So the 2D problems becomes on the line, 3D problems on the surface. But there are some difficulties. So it requires a background mesh. So still you need background mesh and then a smoothing on top of it. So it is harder to code because you've got like this added layer. And that's what I've observed, that for some problems, it is that you lose this benefit over FEM. And the reason is that these methods are very flexible. So you've got so many things to change. So as a user, you have to be aware of this feature. So it could be positive, it could be negative. And I'll finish with this. I believe I've used many techniques, and I believe there is no. You can't say this is like the best technique. There are like different techniques for different applications. It's just like another tool in your toolbox that you can use, in some. And I think I had an acknowledgement page, but just verbally say so. I acknowledge the co-authors. So Omid and Jonas were my PhD students who did most of the coding. Slovak helped us a lot with the bounding surface velocity model. And I also had acknowledgement two senior people, one Professor Khalili, who's always been supportive, and also Professor Jian Liu, who helped me a lot in, like, we had a nice discussion about mesh physics. So with that, thank you.
Yeah, can you go through the slide of change of water pressure and
Which one? Sorry?
the slide of we have the curve of the change of water pressure. Sorry.
I should have
Yeah,
page
go back.
numbers. Sorry.
Go back.
This one?
Continue.
Back?
Yeah. Yes, this one. Yeah. Can you explain me the top and the bottom?
This one? This is the unsaturated media, different permeabilities, and we verified against and this has an analytical solution.
So in your simulation, so can you tell me that what difference between the air pressure and water pressure?
Okay, yeah. The question is about the difference between air pressure and water pressure. So basically, the independent variables at each node, we have displacement for air pressure and for water pressure. We just treat them independently. So they are independent. This is just a variation of like excess for air pressure and water pressure. So we can see their variation independent.
Yeah. So like how much difference between them? Like 10 times, 20 times?
It depends on your problem, your loading. Yes. Yeah, if you ask them what the different, we define that different as a suction, but that suction changes depending on the problem, boundary condition, loading. So that means they can change basically independently, based on the individual problem that you have.
Yeah.
Very nice presentation. Just a quick question on you always have problems when you come with a couple of problems for water pressure. Locking the sort of stuff, working very high sort of fluctuation in the water pressure, and we have to come up with different techniques to stabilize it. With this method, you have it as sort of averaging.
Yeah.
Does that have to stabilize the
Yeah, that's a good question. Look, so you mean this the volumetric locking problem. So when I started, when I read the literature, one of the promise of the method was that it doesn't show volumetric locking. And so, but when I implemented in 2D, in two-phase saturated solid, what I observed is that it doesn't get rid of it completely, but it reduces it. So it is, you still, if you go a smaller and a smaller time step, eventually you get the point that it can handle it. So one of the work that I didn't present it here is that I add stabilization techniques to the method, and it works really good. I can have a discussion with you because, you know, in a stabilization techniques, you have to add some terms, and sometimes those terms can, in finite element method, they cannot be linear because then if you do differentiation, then it becomes a constant. But because we don't have a differentiation, we can stabilize even with simple linear terms. But I didn't present it, but they still need that, so it doesn't, yeah.
Thank you.
Okay, thanks, Salman. We must move on. So.